So now let's write down the parameters. In the question we are given the weight of mass to be 35 kilogram, weight of water was 25 kilogram, initial temperature was 23 degrees Celsius, and we don't know the final temperature. Okay. So the question says a non-conducting container filled with 25 kilogram. The non-conducting then means that the boundary is what is adiabatic. That means there is no transfer of heat between the system and the surrounding. So in that case, the work done will be equal to the change in potential energy, because there is no transfer of heat. So the work done is only going to be equal to the change of potential energy, and we know potential energy is equal to mg times the change in height, and the mass was 35 kilogram times acceleration due to gravity has 9.8 meter per second square times the change in height, which is 5 meters. And when you do that, you are getting the work done to be 1715 joules. And the B says the thermal energy change of the water. From the first law of thermodynamics, change in thermal energy is equal to heat plus the work done. But since the boundary is adiabatic, that means it's not conducting, there will be no transfer of heat. That means the transfer of heat, or the heat which is Q, will be equal to 0. And so in that case, if Q is 0, the change in thermal energy is only equal to work done. So change in thermal energy will also be the same as 1715 joules. The third question, which is C, say the final temperature of the water for which Cp is equal to this. So here we know that since the work is done on the system, its internal energy is going to increase, not because of the transfer of heat. Whenever work is done on a system, the internal energy increase. When heat is transferred to a system, the internal energy also increase. So we have two ways by which internal energy of a system can increase. It's either by adding heat, or doing work on the system. And in this case, we know that the heat addition or subtraction is 0, but work was done on the system, so the internal energy is going to increase. And we can get the change in internal energy by using this formula: M is equal to Cp times change in temperature. So we can calculate for we know change in internal energy, we know the mass of the water, we know the specific heat capacity of the water, but we don't know the change in temperature. So we can calculate for the change in temperature using this change in temperature, make change in temperature the subject. We will get the change to this. Now we don't want the change in temperature, but we rather want the final temperature. And you know, change in temperature is equal to final temperature minus the initial temperature. We don't know TF, but we know the initial temperature. It was given to us in the equation to be 20 degrees Celsius. So after getting the change in temperature to be 0.016, we can then calculate for the final temperature using this. So we just make TF the subject. So TF will be equal to 20 degrees Celsius plus this, and we are getting 20.016 degrees Celsius. That's the D. And the D says the amount of heat that must be removed from the water to return it to its initial temperature. If we work on the system and the internal energy increased by some amount, in order to bring the system back to that exact temperature, we just have to remove the same amount of energy. So it will also, the amount of energy that must be removed will also be equal to the change in internal energy, which is 1715 joules. So it will also be the same thing. And the last one says the total energy change of the universe because of 1, the process of lowering the weight, 2, the process of cooling the water. You know, from the first law of thermodynamics, the total energy change is always constant. So if a system gains heat, it means the heat is lost from its surrounding. And if a system loses heat, that means the heat will be gained by the surrounding. So here we have a system, and we have a boundary separating the system, and we have the surrounding. The system together with the surrounding is what we call the universe, and the total energy in the universe is always constant. So whether a system is losing or gaining heat, the total energy in the universe is going to be constant. So from the first process, lowering the heat, it doesn't affect the total energy in the universe. So the total energy in the universe will always be constant. So the change in energy in the universe will always be 0. So the second process is 0, the third process is also 0.